All right, this is our remainder comparison worksheet because we now have two theorems that help us find a remainder or an error bound, or basically how accurate our approximation could be. So the first one was the alternating series remainder theorem. This is where if you have a series whose terms are actually alternating between positive and negative every other term, then you don't really need the Lagrange error bound. You can just use the alternating series remainder theorem, which says that the largest error you will ever have is that first neglected term. So if you use a third order uh, polynomial to approximate a series, then the fourth term is the largest possible error. And that is an absolute value, by the way. All right, so this says find a fifth order Maclaurin polynomial, so C is 0, that approximates sine of 2x equals f of x. So we need to build this thing first, and eventually they will ask us about the remainder. So just find the fifth order polynomial. All right, so I always start with f of x, defining that. It's sine of 2x, and then we need to evaluate that at 0. Sine of 0 is 0. F prime of x, remember to chain rule here. The derivative of sine is cosine, and there will be a 2 that gets pulled out. So 2 cosine of 2x. And then f prime of 0, cosine of 0 is 1. 1 times 2 is 2. We need to take this out to 5 derivatives. So f double prime will be negative 4 sine of 2x. F double prime of 0. Sine of 0 is 0, so that'll be 0. So you can see every other term is going to be 0. The third derivative will be negative 8 cosine of 2x. The third derivative at 0 will be negative 8 times cosine of 0, which is negative 8 times 1. The fourth derivative will be positive 16 sine of 2x. The fourth derivative evaluated at 0 will be 0. And the fifth derivative will be 32 cosine of 2x. And the fifth derivative at 0 will be 32. All right. So we're going to build this fifth order Maclaurin polynomial. So we're saying that the sine of 2x is going to be approximated by f of 0. So I'm going to fill in the zeros. You don't have to, but 0. And then it's plus 2 times x plus 0 x squared over 2 factorial. I mostly am just writing the 0 so I don't miss something. Minus 8 x cubed over 3 factorial plus 0 x to the fourth over 4 factorial plus 32 x to the fifth over 5 factorial. You do not have to write the 0, so it's totally fine to simplify this and say, okay, so 2x minus 8x to the third over 3 factorial plus 32x to the fifth over 5 factorial. I'm going to call that my fifth order Maclaurin polynomial. Okay, and then we'll use a calculator for this. Use this fifth order Maclaurin polynomial to approximate f of 0.1. So I'm going to plug that into my calculator. Oh, that's not my calculator. There we go. So let's see. 2 times, what is it? 0.1. 2 times 0.1 minus 8 times 0.1 to the third divided by 3 factorial is 6 plus 32 times 0.1 to the fifth divided by 5 factorial, or I know that one is 120. I'm going to write down this whole decimal. I don't really want to round it because I want to see how accurate it is. So 0.198669, 3 repeating. Use the alternating series remainder theorem to find the error boundary of B. So now you don't have to write the whole formula out either, but remember the alternating series was just saying this f of x, if I extended this for infinitely many terms, there would be an actual sum for this. So whatever the sign of 0.1 actually is, minus our approximation, P5 of 0.1, there's some sort of error there. It's equal to the remainder of the fifth order approximated at 0.1. And we know that that's less than or equal to the sixth term in absolute value. So it's just what would the next term have been that you left off. So you just need to find what the sixth term would be. So that means I do have to do a little bit of work here. What would the sixth term have been? So I need to find the sixth derivative. So the fifth one was back here, 32 cosine of 2x. So the sixth one would have been negative 64 sine of 2x. Okay, and then evaluated at 0. Now the sixth one would have been 0. Well, I can't say 0. The error is less than 0. That doesn't work. So what's the first neglected non-zero term? So actually I have to push it out to 7. All right, so what's the seventh derivative going to be? It's going to be negative 128 cosine of 2x. And the seventh derivative at 0 is going to be negative 128. All right, so, or maybe you're just following the pattern. Like you can see this is 2 to the first, 2 to the third, 2 to the fifth. The next one's going to be 2 to the seventh, which is 128. And it'll be over 7 factorial. All right, so actually that's going to be 7. So it needs to be less than or equal to 128, because we're in absolute value, times 0.1 to the 7th divided by 7 factorial. What does that come out to? 128 times 0.1 to the 7th divided by 7 alpha window factorial. So again, I'm going to write this down without rounding it. So this comes out to, there are 8 zeros here. Right? And what is the actual sign of 0.2? I'm in radian mode. It's this value. So remember, this was my approximation. This tells me, my error tells me I should have at least 8 decimal places that match up. So 1, 2, 3, 4, 5, 6, 7, 8. I do. It's only the last 2 that don't match up. So that's perfect. So this sign is 0.19866933308. All right, so Lagrange error bound. This little phrase here, I don't want to get confusing. This is like another way to think about why we're able to say z is sitting between 2 values and how far off we have to be. I think this is confusing. I think I'm confusing when I explain it, so I'm nixing that. Here's a reminder of what Lagrange error bound is. In absolute value, you figure out the max n plus 1 derivative. If this is sine or cosine, if that's f of x, then the max is 1. Otherwise, you have to find the pattern and plug in z being between x and c. Okay, so find the Lagrange error bound from above. All right, so the Lagrange error bound from above, again, we used a P5, right? So we're saying, all right, let's let Lagrange have a crack at this. So the sine of 0.2 minus the P5 approximation of, was it 0.2? I thought it was 0.1. Oh, yeah, it was 0.1. But it was 0.1. But this was sine of 2x. So back here, that should say 0.2. Okay, anyway, minus P5 of 0.1 is equal to absolute value remainder of a third order approximation less than or equal to fn plus 1 z times 0.1 minus the center 0 to the n plus 1. No, not to the n plus 1. We have n plus 1. To the 6th over 6 factorial. Now we do this, even though I know that that 6th term is 0, we are going for max error. So we're not going to skip over to the 7th one like the alternating series does. It's not the first neglected term. It's what would the max possibly be. So even though we know the 6th derivative is 0, we're not going to do that. We're going to say, well, it came from a sine function, so it could have been 1. So f6, I know f6 is, what was it, 64? Yeah, it's 64 sine of 2x. The max that this could be is 1, and we have a 64 out in front in absolute value. So the max this could be is 64. Not just 1, because there's an extra coefficient out in front. All right, so this is 64 times 1/10 to the 6th over 6 factorial. So that's 64 over 10 to the 6th times 6 factorial. Let's go ahead and just do that in the calculator. 64 divided by 0.1 times 6 factorial. Wait a minute, what happened? Oh, 0.1 to the 6th. I was going to say that's a pretty bad error. 0.1 to the 6th times 6 factorial. No, what happened? Okay, hold on. Clear this out. 64. Let me see if I can type this in correctly. 64 times, oh, I had the 0.1 in the wrong spot, times 0.1 to the 6th. I'll get it right. Divided by 6 factorial. There we go. That looks better. We need to have a bunch of zeros in front for error. It's bad if your error is like 8,000 and something. Okay, so this is 7 zeros. 2, 3, 4, 5, 6, 7. And then it says 8 repeating. So this is a more conservative error bound. This is saying we're only going to have 7 decimal place accuracy, whereas alternating series remainder, because it took us out an extra term to get to a non-zero term, that said we're going to have 8 decimal place accuracy. We actually did have 8, but sometimes they're different. Sometimes they would be the same. So it just depends on what the function is and if the maximum actually is the value, like the function value that you get when you're evaluating. All right, number 2. We've already found that this is one of the ones that we memorized or had in our little box to memorize. We already found that 1 over x plus 1 is about equal to this it's a geometric series. 1 minus x plus x squared minus x cubed plus x to the 4th. I think we had 1 over 1 minus x in our what was it called? In our notes. So this would be like if r is negative x. Okay, so that's the 4th order polynomial for this approximation. Use this to approximate f of 0.2. All right, so f of x is actually 1 over x plus 1, but we're going to approximate f of 0.2 using this function right here. So 1 minus 0.2 plus 0.2 squared minus 0.2 to the 3rd. You don't need the parentheses because you're not plugging in a negative and raising it to exponents. So I get this value. Okay, then find the Lagrange error boundary. All right, so what is the difference between actual f of 0.2 and my 4th order Taylor polynomial at 0.2? It's equal to the 4th order remainder at 0.2, which is less than or equal to the maximum of the fifth derivative at z, which is sitting somewhere between 0.2 and the center, which is 0. And I can see that because these are just x's. It's not x minus something. Times x, 0.2 minus 0 to the fifth, over 5 factorial. So I need to come up with what is this f5 of z. So let's see. Now, I could take a bunch of derivatives, but there's a reason this is being shown to me. This is f of 0. This is f prime of 0. This is f double prime of 0 over 2 factorial. This is f triple prime of 0. This is f to the fourth of 0, fourth derivative. So what's the fifth derivative going to be? These are factorials on top. 24 is 4 factorial, 6 is 3 factorial, 2 is 2 factorial. So the max f5 of x, well, the f5 of x is going to come out to be 5 factorial over, what would it be? We would have had an x plus 1 to the fifth, right? Because if you actually are taking derivatives here, you would have had, before you plugged in 1, you would have had, this is x plus 1 to the negative 1. Take the derivative of that, you get 1 over x plus 1 negative to the second. Take the derivative of that to the third, to the fourth. So now if you can't get here, then go ahead and take all the derivatives until you get to the fifth one. But this is the formula for the fifth derivative. And then what are the options? The options are either plug in 0.2 or plug in 0. So in one case, you have 5 factorial over 1.2 to the fifth. And in the other case, you have 5 factorial over 1 to the fifth. And this is bigger because you're not dividing it by 1.2 to the fifth. So I'm going to replace f5 of z with 5 factorial. This is just 0.2 to the fifth divided by 5 factorial. 5 factorials cancel out. So it's actually 0.2 to the fifth is our Lagrange error bound. So that's what? 1/5 to the fifth, or I could just 0.2 to the fifth is 0.00032. Find the alternating series remainder theorem error. This one's going to be the same because what is the next term that we leave off? The next term, oh, you know what? I didn't even have to do all of that. Why am I? Oh, no, yeah, I did. The next term that I would leave off is minus x to the fifth. So the fourth order remainder would have been less than or equal to the fifth term in absolute value. Evaluated at 0.2. And the fifth term that you're leaving off is x to the fifth, so 0.2 to the fifth. So I get the same thing. So sometimes Lagrange and alternating are the same, and sometimes they're not. F of x equals radical x centered at x equals 4. Find the second order, n equals 2, Taylor polynomial centered at 4, so c is 4, and then approximate, we're going to use that to approximate f of x. So first off, we need to get to just 2 derivatives, so that's pretty nice. So we're going to need, lost my pen again. We're going to need f of, we're centered at 4. So f of x is equal to radical x. F of 4 is equal to 2. And then f prime of x is 1/2 x to the negative 1/2. So that's 1 over 2 radical x. F prime of 4, 1 over 2 times 2 is 1/4. And we only have to get to second order, so last derivative to take. So this is 1/2 times negative 1/2, so that's negative 1/4. And then x will be to the 3/2 in the denominator. And when you plug 4 into that, you get negative 1 over 4 times, so square root of 4 is 2, 2 to the third is 8, so negative 1 over 32. All right, so we're saying square root of x can be approximated by 2 plus x minus 4 to the first over 4. minus x minus 4 to the second over 32 times 2 factorial. It's easy to forget the factorials, so if you're worried about that, write out the previous step where you set it up. F of 4 plus f prime of 4 times x minus 4 over 1 factorial minus f double prime at 4 times x minus 4 squared over 2 factorial, and you just set it up before you plug in your numbers. Okay, now approximate f of 3.8. So let's head over to our calculator. So 2 plus 3.8 minus 4 is negative 0.2. And I would need that in parentheses. Well, I guess not for this first term, but when I'm squaring it, I do. And the 32 times 2, or just do 64. 32 times 2 would need parentheses around it if you're doing it that way. So I get 1.949375. Let's check to see if we're even in the ballpark. What if we screwed something up? That looks pretty good. Okay, I'm confident so far. All right, use the Taylor remainder to find the error boundary for part B. So we want to find the difference between the square root of 3.8 and our second order approximation at 3.8. That's equal to the second order remainder at 3.8, which is supposed to be less than or equal to the third derivative at z, whatever that max value is, times 3.8 minus 4. But you know what? We're doing this in absolute value, so let me just spin it around so I don't accidentally put a negative, to the third over 3 factorial. So what is that third derivative? So let's see. The third derivative of x, so going off of here, the third derivative would have been negative 1/4 times negative 3 over 2. So that's positive 3/8. And then you're subtracting 1 from the exponent again, so it's going to be x to the 5 over 2. And your choices for z are between 3.8 and 4. So we're comparing 3 over 8 times 3.8 to the 5 halves versus 3 over 8 times 4 to the 5 halves. Now this is a smaller denominator, so it's a bigger fraction overall. So that is what we're putting in for the max value here. So that's kind of ugly, right? 3 over, this is 0.2 third. This is 8 times 3.8 to the 5 halves. And don't forget about the 3 factorial that's down there. What does this come out to? I think I'll use my little fraction key for this one. 3 times 0.2 to the third, and 8 times 3.8 to the 5 halves, and multiply it by 3 factorial, or I'll just put in 6. I think putting in 6 is fine, but I'm going to put in times 6. Okay, and this is 4 decimal place accuracy. It's probably fine to round these, by the way, after you get to 3 places. I just like to write it all out. All right. Yeah, so we're saying accurate to 4 decimal places. Okay. Use the alternating series remainder to find an error bound. So the alternating series remainder just says, what is this missing term? What would you have plugged in next? So what would have come next? Well, we found our formula for f triple prime of x. It was 3 over 8 times x to the 5 halves. And remember, in the next term, you're evaluating that at 4. You're not going 3.8 versus 4 or whatever. So what would that be? That would be 3 over 8 times 2 to the 5th, 32. All right, so the alternating series remainder would say R2 of 3.8 would be less than or equal to A3 of 3.8. And what would that term have been? So we just said here's f triple prime, so it'd be this, whatever that is. And then it would have been times x minus 4, so 3.8 minus 4 to the third power over 3 factorial. All right, so let's see what that comes out to. So actually, I want to keep what I had on there before. Okay, so let's do this one now. So 3 times 0.2 to the third, that's the same. And then right here, we have 8 times 32 times 6. A little bit different, right? Because instead of 3.8 to the 5 halves, we had 4 to the 5 halves. All right, so I'm going to write this down. 1, 2, 3, 4, 1, 5, 6, 2, 5. They will tell you which error bound to use. If they don't come right out and say alternating series remainder theorem, then they will say something like the terms in this series are alternating in sign and decreasing towards 0 in value, and that's your green light to use the alternating series remainder as well. All right, what is this question? Y equals sine x. Find a fourth order Maclaurin polynomial and use it to approximate f of 0.1. Now you could go through the work of finding it, or maybe you have this one memorized? Question mark. This is the one that has the odd values of sine. So sine x can be x minus x cubed over 3 factorial. Now the next one is plus x to the fifth over 5 factorial, but the fourth order would have been 0, x to the fourth over 4 factorial. So this is the fourth order Maclaurin polynomial for sine x. And then use that to approximate f of 0.1. So plug 0.1 into that. So 0.1 minus 0.1 to the third divided by 6. So that's 0.0998. 3 repeating. Find the Lagrange error boundary. So we are looking for the difference between actual f of 0.1 and our third order approximation at 0.1. That's equal to the remainder at 0.1, which is less than or equal to the max of the fourth derivative times 0.1 minus 0 to the fourth over 4 factorial. Good news, f of x is a sine or a cosine. So the max is 1. So I'm putting a 1 in here. So I have 1/10 to the fourth, or 1 over 10 to the fourth, times 24. So max error on this one is 1 over 24 with 4 zeros. That could be a non-calc problem. Okay. Oh, nothing else to do with that one. Okay. Oh, this one's interesting because they give us, we don't have a formula to go off of. So find a third order Taylor polynomial centered at 2 to approximate f of x. So we don't know what f of x is. But remember, we can build it. These are the pieces to build it. So f of x can be approximately f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 squared over 2 factorial plus f triple prime 2 times x minus 2 to the third over 3 factorial. Oh, and that's it, third order. Use it to approximate f of 2.1. Okay. So 3 minus 2 times 2.1 minus 2 is 0.1 minus 0.1 squared divided by 2 plus 4 times 0.1 to the third divided by 6. So 2.7956 repeating. Find an error boundary. Can't use alternating unless told. Okay, they didn't tell me to use alternating, so I'll use Lagrange. So we're looking for what's the difference between actual f of 2.1 and this third order Taylor polynomial approximation. That's the remainder of a third order evaluated at 2.1. That's less than or equal to the fourth derivative at z, max value of that, times 2.1 minus 2 to the fourth power over 4 factorial. How do we figure out the max fourth derivative at z? They tell us this, and this happens a lot in the free response questions. They will give us a maximum, and we just put it in there. So 21 is the max. And we just calculate this. So this is 21 over 24 times 1/10. I'm just going to put it in my 21 times 0.1 to the fourth divided by 24. So 0.1234875. All right. That finishes this worksheet. So hopefully you're getting a little bit of the hang of the formula. I know it can get a little confusing. So I do suggest I keep writing it out like this just to try to give myself like a process that I always follow. I think that's helpful when we're in some of these topics that can get confusing.